Good morning, everybody. We start our meeting. Alvaro is going to co-host the meeting. You can ask him questions during the presentation, and I'll be available at the end of the presentation again to answer any extra questions. So we start immediately by sharing the screen and getting into our website here. I have to adjust the screen here a little bit. We get to our site, and last time we started covering the chapter on the birth of the nuclear age through the Chicago pile number 1. And as we described it, it was followed immediately by realizing that two isotopes, the uranium-235 as well as the uranium-235, can be used in producing a tremendous amount of energy. And the release of energy from the nuclei is at the same level as the discovery of fire and for humanity. And of course, unfortunately, the first use of it was in a destructive fashion in terms of its use in the bombings of Hiroshima and Nagasaki. We defined last time the energy release that is produced from nuclear reactions or fission, and it is in the level of not just the 13.6 ionization energy of the hydrogen atom, which is characteristic of chemical reactions. Here we are talking about a release of 10 to the 12 calories, or the equivalent of 1 kiloton or 1,000 tons of the explosive TNT, the TNT equivalent. And let us go through the exercise of estimating that number here in calories, and then getting it also in terms of a mass of how much fissile material, in that case uranium-235 or plutonium-239, can be released. So bear in mind here now that a fission event can produce 200 million electron volts of energy, whereas a chemical reaction produces only 13.6. So it's not just an order or 2 orders of magnitudes energy release in nuclear reactions compared with chemical reactions. It's orders of magnitude in that case. It turns out that we define 1 kiloton of TNT as 10 to the 12 calorie. We can turn the calories through simply using the units here. 1 calorie is 4.2 joules per calorie. Then that turns into the calories into joules. 1 joule is 1.6 10 to the minus 19 electron volt. We divide into that number, we get now units of energy in electron volt. We turn the electron volt into million electron volts, which becomes 10 to the minus 6. And we showed in a previous table that the fission event produces 200 million electron volts of energy. But if we account for the antineutrinos that we cannot really extract, they can travel through the whole Earth without interacting, then in that case, you find that this is equivalent to 1.45 10 to the 23rd nuclei. We cannot measure this in the laboratory, obviously, but of course, we are using our intellect here to do the calculation. Now, how much is that in the mass of a fissile material? In that case, we use a very famous law from physical chemistry, which is named after its discoverer, Mr. Avogadro, or Avogadro's law, that tells me that in a mass G of any material in grams, if we calculate the gram molecular weight or the moles, the number of moles, by dividing the mass in grams into the atomic mass in atomic mass units, this would be the number of moles, that each mole contains a constant of nature here, which is Avogadro's number. It's 0.6 10 to the 24th nuclei per mole, I can solve for G here, the mass, it becomes N, the number of nuclei, multiplied into M, the atomic mass, divided Avogadro's number in grams. So if we said earlier that the 1 kiloton of TNT is 10 to the 23rd nuclei, then that is my capital N, and we substitute here and we discover that 1 kiloton, 1,000 tons of equivalent TNT, trinitrotoluene explosive, can be generated from just this tiny amount of mass, 57 grams, or you can turn it into 2 ounces. And that shows us the very high specific energy inherent in nuclear processes compared with any chemical type of reaction. Let me change the view here, the gallery maybe, or the speaker, whichever. All right, so let's go to sharing the screen again. And in that case, you could see that a very small amount of mass can be converted into a tremendously large amount of energy. By the way, later on, we will discover that energy itself can undergo a reverse process, in that, say, gamma radiation with a very high frequency material can turn into a mass. All right, so this basically discusses how it is that a nuclear explosive cannot, a nuclear reactor cannot explode like a nuclear explosive. We might come back to this later on. But now, with the testing of the plutonium-239 in the Trinity event that we explored last time, nuclear energy was now ready to be used, and the usage did not come first in the peaceful applications we are talking about, but it happened in war. So how did that happen as a process? With uranium-235, uranium-235 can be separated with a tiny amount of uranium-234, but plutonium-239 can be separated chemically with a significant amount of plutonium-240. Plutonium-240 undergoes a spontaneous fission process, so it generates neutrons, and we cannot simply bring in 2 masses of plutonium-239 together to create a critical mass and get an explosive kind of a reaction. For uranium-235, the 234 is not very reactive radioactivity-wise, so we can basically create a critical mass and create a chain reaction by getting 2 subcritical masses of that uranium-235 together. So the idea here is to use simply a gun barrel, surround that uranium-235 with a temper, maybe lead, it may be uranium, it may be even gold, and then bringing in those 2 pieces together, you'll find that now there is enough of a critical mass, like in the case of the Chicago pile number 1, to create a chain reaction. And that process, in fact, was used in the bomb that was used against Hiroshima in Japan, the first ever use of nuclear energy in warfare. Or you can have a subcritical mass stationary in a gun barrel, and then shoot another subcritical mass into it. You create a critical mass. One interesting aspect of the process is that the Germans thought that, remember, fission was discovered in Germany. They had a nuclear process where they tried to get a sustained chain reaction, but they thought that that chain reaction can only be obtained with the use of a moderator, like the Chicago pile number 1. It was a genius of Enrico Fermi again, and the other scientists brought in to the United States from Europe, that, oh, you also can create a reaction not just with the existence of a moderator, but without the existence of a moderator. In that case, use fast neutrons to generate the reaction. That was missed by the Germans with their leader, Werner von Heisenberg. The other approach, of course, is to bring in subcritical mass into another one by shooting it into the mass. And another configuration that was suggested is that you'd get a subcritical mass of uranium-235, and you shoot from the gun barrel with a piece of temper there, another mass that makes it supercritical. The temper is there to contain initially the gases from the reaction and keep the fission fuel together without its dispersing prematurely. And I need here to adjust the page probably. Oh no. I lost the screen now give me a chance to try to recover here. Okay. In fact, some people have shown us this is a replica of the device, in that case, that used the uranium-235. And this is a picture of the actual device that was dropped on Hiroshima. People suggest that a configuration would be to have 3 rings here with an absorber in between them. Then you'd have a gun barrel. You shoot a uranium projectile, uranium-235, with a propellant like any shell in a gun. And before you do the process as a matter of safety, you bring in those 3 target rings together. So this would be arming the device, and then you shoot that uranium-235. You remove out the absorber there and the boron carbide that would be a good absorber for neutrons. And it's just like boron, of course, is a good absorber for neutrons. So you have to provide lots of safety features so that you don't have a premature explosion, let's say on an airplane or a rocket that is delivering the weapon. The uranium-235 was very hard to obtain. In fact, we'll see later when we calculate its critical mass that it's about in the range of 50 kilograms. Whereas later on, we'll see that plutonium is only 10 kilograms. So there is a suggestion that only a few devices, or maybe only one, was used that uranium-235. Plutonium-239 is much cheaper in that case. Remember, uranium-235 was used through the process of the Calitron electromagnetic separation, as well as gaseous diffusion at Oak Ridge, Tennessee. The plutonium-239 device was tested, and in that case, it requires the process of implosion. And the implosion in that case would consist of explosive lenses, with now the plutonium-239 enclosed inside a temper. You would have a casing on the outside, maybe uranium-238 or lead. And what you do is that those explosive lenses would explode and bring in, implode the core of plutonium-239. The nuclei come in very close together. They surmount their Coulomb repulsion, and they fuse together. This can be done with a solid core, or it can be done with a shell of the plutonium-239. The explosive lenses provide really an implosion process. We'll study it later on, because the same process is being used in what we are going to call inertial confinement fusion. Or you can have a porous material of plutonium-239 and implode it to the center. That one, of course, was tested in the Trinity test that we covered last time. But in fact, there was enough of it available. And after the Trinity test, so it was used on the city of Nagasaki in Japan. And that practically ended the Second World War. There is a debate among scientists and historians about whether there was a need to use it or not. Japan was suing for peace. Japan was worried about the Russians entering the Second World War against Japan, and they had their eyes on annexing the northern Japanese islands. So the United States basically accepted the surrender of Japan, and that ended up the Second World War that continued in the Pacific. And ironically, the fission reaction that was discovered in Germany was never, the devices were meant to be used on Germany, but that was never used since Germany had surrendered. And the debate went on whether it should have or should not have been used against Japan. This is actually the device that was used, an actual picture of the device that was used on Nagasaki. It used the implosion process on the plutonium device, and they gave it a code name. They called it Fat Man, but it shows here that an implosion process was used. That device generated 21 kiloton of TNT equivalent, thousands of tons. And the little boy device, that was the one that was used on Hiroshima, or the gun barrel concept shown here earlier, generated only 15 kiloton of energy. So its efficiency was lower in that case. The little boy bomb design had 64 kilograms of uranium enriched to an average level of 80%, meaning that through the isotopic separation process, it was 80% uranium-235. You'll see later that enriched fuel of uranium-235, at least used in nuclear propulsion of submarines and aircraft carriers, can reach the level of 93 or 94%. And apparently, the United States built only 26 of those little bomb designs, and that was basically a mass production on a large scale. But later on, it became, that device produced 15 kiloton of power in general. Nuclear power plants use today 3 to 5% enriched uranium. There is no reason it has to be 3 to 5%. It was some number that was simply adopted and remains historically used as a suggestion by Admiral Hyman Rickover, who started the nuclear navy. He didn't want to have highly enriched uranium that is used, in fact, in naval propulsion reactors, available in the hands to many people. And the whole level of enrichment, low enriched uranium, has remained so far in all the power industry. Research reactors would use an enrichment of 20%. Research reactors produce isotopes for medical and biological type of applications. And the IAEA, the Nuclear Non-Proliferation Treaty, commits nations of the world, the signatories to the NPT, or Nuclear Proliferation Treaty, not to enrich their fuel beyond the 20% level, which would make it suitable supposedly for weapons design. The little boy design generated 15 kiloton of TNT equivalent, and it was a very low efficiency. It burned only 1.5 pounds of that uranium content, but the device overall was 4 to 5 metric tons. So it was really a very tiny amount of the mass that was turned into energy, and here it is shown. The little boy produced 15 kiloton. Again, that's an interesting number, whereas the Fat Man produced, the plutonium device produced 21 kiloton of energy. So primarily, plutonium is being used today in nuclear devices. The Hiroshima bombing, of course, occurred. This is a picture from the plane that dropped the device on the left side. That is from the Hiroshima device. You could see here the city at the bottom. It caused, of course, a massive fire that burned almost everything. But the United States has used also fire bombing on other cities in Japan, like Tokyo, for instance. Fire bombing with conventional explosives also was used in Germany on Hamburg and Dresden. And this is the mushroom from the device that was dropped on Nagasaki. The Hiroshima device was dropped on August 6, 1945. The one on Nagasaki only 3 days later, on August 9, 1945. They used a very large bombers, and the one that carried the little boy was a B-29, Boeing B-29, and it was its pilot named the plane as Enola Gay, and basically the name was after his mother, his mother's name. And you could see here the actual device that was dropped on Hiroshima being loaded into that B-29. It was a very large weight at the time. Today, those devices are very much miniaturized. The process generates, as we know, neutrons from the fission process, X-rays, and the X-rays get absorbed in any dark material, and that causes fires. Here is a picture of the survivors. These people survived the bombing, but you could see that the X-rays were absorbed in parts of the dress that were dark, so that caused burns. So that lady survived. These are two other people. The Japanese named them the Hibakusha, the burn victims from the Hiroshima explosion. The devastation was tremendously large. You could see here, it caused not just a shock wave that destroyed the structures, but also caused fires all over the place. And this is a picture of a fire engine that could not help, of course, extinguish the fire. The devastation at what is named today as Ground Zero was large. Some concrete structures survived the bombing, but the rest of the structures in the town was a total devastation. That's 4,000 feet from Ground Zero. It was a dilemma. The dilemma was that it's not just fires that were initiated, but also the X-rays and the gamma rays and the neutrons irradiation of the population. What survived is a concrete structure. It was a theater there, you could see it, and that has been kept as a memorial. It is named now the Peace Dome. It is what's called the Genbaku building. It was a movie theater. The Japanese kept the skeletal structure of it as a memorial to the bombing and the victims of Hiroshima. President Obama gave a conciliatory kind of speech in Japan, and right now that Genbaku building is UNESCO World Heritage site. So if you visit Hiroshima, you can visit the place there. These are other pictures of the devastation of the Hiroshima site. It was followed by people simply rummaging through all the destroyed buildings. The aftermath effects are simply were tremendously large. The bombing of Nagasaki was done by another B-29. It was named the Boxcar. So the pilots there would give names to their B-29s, and this is the actual bomb being loaded onto the B-29, Boeing B-29, and the parts were assembled at the Tinian Island, and they were sent there by a cruiser named the Indianapolis. We'll come back to it at the end. It had its own tragedy other than the bombings in that case. Because Nagasaki had hills surrounding it, the devastation was less, but similar to Hiroshima, that it had a very large fire effect, and parts of the concrete structure of a Catholic cathedral on the left and the Buddhist temple on the right remained, and as remnants of the explosion after the explosions. This is a devastation that happened at Nagasaki, the ground blasting effects, and again at ground zero. Some details about both bombings can be read here. Again, you'll find that the radius of destruction depends on the yield of the device. So if you are using a 10 kiloton device, you can generate a fireball that would be 200 meters in size, or twice the size of an Olympic swimming pool. If you raise the yield to 100 kiloton, which is used today as almost a standard for strategic weaponry, that fireball could be 500 meters in diameter. 1 kiloton device is only 10 meters in diameter. The shock wave that is generated, or the blast wave, also depends on the yield. And some people put this into some equations for the radiation radius, the blast shock wave radius, and the thermal infrared. Infrared means that that's heat now that causes, of course, fires. So in addition to shock wave destruction, you get fires generated and burn the remaining material from the explosion. The casualties that happened at Hiroshima and Nagasaki have been estimated. Depending on the population density, Hiroshima had a lower population density than Nagasaki, but in Hiroshima, there were 70,000 people affected as victims on a short term from the explosion itself, but the effects of radiation that occurred, like causing leukemia, for instance, and long term, it's double the amount, 140,000 people killed. Nagasaki had 36,000, and but the fire bombing had happened earlier on the rest of the Japanese cities, and in fact, the bombing, the incendiary or the fire bombing of Tokyo caused much more deaths than the Hiroshima and Nagasaki. Tokyo fire bombing caused the deaths of 83,000 people, and basically that was 93 attacks on Tokyo using 1,129 tons of TNT and incendiary bombings. The mortality per square mile, though, as you could see here, is much larger in nuclear devices, 15,000 per square mile victims per square mile. Nagasaki, 20,000. Tokyo, the fire bombing was only 5,000 in that case. So conventional weapons can cause as much, well, less damage than nuclear devices, but nevertheless, they are usable in war. The casualties per square mile at the Tokyo fire bombing was 12,000 per square mile, but at Nagasaki, it was 42,000, Hiroshima, 30,000. And so that was, unfortunately, the first use of nuclear energy in war. But the fire bombing is still an option for the military. This is a picture of what happened in Germany at Dresden. So that fire bombing resulted in much more than the victims in Japan. That was in 1945, February. It wasn't August, but February 1945. That resulted in 600,000 victims. When you cause a fire bombing using incendiary devices, you generate a firestorm. The heat of the explosion sucks the air up, and basically victims, even those who were in shelters underground, were suffocated to death. They had no air to breathe. So the damage that can happen from conventional warfare is less than nuclear devices, but nevertheless, both of them are killers of humans. That happened with the B-29 fortresses in 1945. They dropped 2,000 tons of napalm and magnesium incendiary bombs on the timber and paper houses of Akazuka. Officially, 83,793 Japanese were killed. It was a very nasty situation in that case. That was followed by a meeting of the Allies in Yalta. And Potsdam, that is history that you may like to read about. And basically, they divided the, the spoils of the war among the winners in that case. The tragedy on Hiroshima and Nagasaki had it was continuous in terms of whether it should be used or not be used in the United States. The argument that won the day was that, all right, we use the devices to end the war and reduce any possible casualties among both military in Japan and the United States, as well as as reducing the civilian death. Something happened beyond it, and if you watch the movie, let us see here. This is the bombing of Hiroshima and Nagasaki were followed by another tragedy of the cruiser, USS Indianapolis cruiser. It had sailed 5,000 miles carrying the components of the uranium-235 device, and people in the United States Navy didn't know its whereabouts. It was kept secret, and after delivering the parts and the weapon being of course put together and dropped on Japan, the cruiser started getting back on its travel back. As this was traveling back, it had a crew of about several thousand people here, and it was sunk by a Japanese submarine. And on July 30th, 1945. So that was before the bombing occurred. And the Navy didn't know where it is because the travel was kept secrets, and carrying the components to be assembled on the Tinian Island. And for several days, the crew was in the water, and the captain of the ship was named McVeigh, and the blame was put on him on why he did not go in a zigzag pattern to avoid being intercepted by the Japanese submarine. A very, very harrowing situation happened with the crews in the water. They were eventually discovered by a reconnaissance plane, but the movie, there was a movie about it. Let me see what's the name of the movie. I forgot the name. If you watch the movie, it tells the story, and it was sunk by that submarine, and 4 days later only rescues operation started, and it was a harrowing experience. Captain Charles McVeigh committed suicide. He received some nasty mail, but in the year 2030, 2 years after he committed suicide, he was absolved of the charge of negligence as an act of the United States Congress, and graded his name. Anyway, the discussion here, Japan's attack on Pearl Harbor may have, of course, initiated as a response to President Theodore Roosevelt sanctions on Japan, same sanctions as we are imposing on Russia today have been imposed on Japan. Any imports of oil, petroleum to Japan were simply banned, and the Japanese simply found that they were had no choice but attacking Pearl Harbor. The history of whether it was should have been done or not is being debated by historians. Japan wanted to basically end the war. They were afraid of the Russians getting their northern Japanese islands. The decision was taken to use a 2 atomic bomb, and that practically ended the war. This is a picture showing Robert Oppenheimer here, where the tower on which the Trinity test of the plutonium-239 was done totally evaporated. This is Leslie Grove, Robert Oppenheimer again. There is a commemorative, and this is another picture from an airplane of the site. So the devastation was there by the Trinity device. The movie that was built around the history of the Indianapolis is named Jaws. You could go and watch it or rent it and watch it. And the people who survived the Indianapolis sinking kept meeting at Indianapolis in the city of Indiana every year to commemorate the event. The Trinity test itself is commemorized in that a memorial right there, and that memorial is open to the public only once a year on the first Saturday of the month of October. So if you find yourself in the area of New Mexico or the Los Alamos National Lab, you may find your way there. In fact, 2 of our students found their way there from our class, the NPRE 402 here that you are attending. One of them brought some sand, molten sand from the desert floor for me to show maybe on the website. And then she said that it disappeared on the airplane. She never found it. Another gentleman also sent me a picture standing next to it who took our class. He was on an Air Force air base in the vicinity. So if you find your way there, you can visit that site on the first Saturday of the month of October. The nuclear age was born in the building of the Chicago Pile number 1, followed by the Manhattan Project, the first nuclear test at the Trinity site, and the first use of nuclear devices against Japan, and that ended the Second World War. The forces that were acquired in knowledge unleashed in these events is sure to affect human life forever. In fact, it is as important as the discovery of fire. The discovery of fire affected humanity's survival, but it is an atomic phenomenon. It happens between the electrons in the outer shell of the nuclei, whereas nuclear energy is another form of discovery of the release of energy from the mass itself of the nuclei. So it's a phenomenon that happened in the nuclei themselves. What the future historians will regard as the most important event of this age would be definitely the release of nuclear energy. The knowledge about it, or the genie, is out of the Aladdin bottle, if you want to create an analogy, and the nuclear age was born in that case. I have appendices added to the chapter that you may like to find interesting and read them on your own. The nuclear milestones in the discovery of uraniums, and Rontgen discovering X-rays, and then Becquerel, and all the scientific milestones are listed here for you to read if you haven't had the chance to see them in other courses or other situations. And I also added an appendix, which were discussions between whether it was necessary to use nuclear weapons on Japan. This is a discussion that will remain ongoing among historians and anthropologists. This is a transcript, a total transcript of President Barack Obama's speech in Hiroshima, according to the New York Times. It was a conciliatory kind of speech. Japan and the United States now are allies, and I hope that they would remain friendly for the rest of time. In terms of whether the bombs should have or not have been used will remain under discussion, but many prominent people like President Dwight, or who was General Dwight Eisenhower, he was the supreme commander of all the Allied forces and the officer who created the World Second Military Plans for Europe and Japan, is noted, and there are other people also who had their own discussion about the bombing and using the nuclear weapons on Japan. And that's what I quote here in an article, Ike on Ike. He noted, he's noted to have said, in July 1945, Secretary of War Stimson, visiting my headquarters in Germany, informed me that our government was preparing to drop an atomic bomb on Japan. I was one of those who felt that there were a number of cogent reasons to question the wisdom of such an act. The secretary, upon giving me the news of the successful bomb tests in New Mexico, that's a Trinity test, and of the plan for using it, asked for my reaction, apparently expecting a vigorous assent. During his recitation of the relevant fact, I had been conscious of a feeling of depression, and so I voiced to him in my grave misgivings, first on the basis of my belief that Japan was already defeated and that dropping the bomb was completely unnecessary, and secondly, because I thought that our country should avoid shocking world opinion by the use of a weapon whose employment was, I thought, no longer mandatory as a measure to save American lives. It was my belief that Japan was at that very moment seeking some way to surrender with a minimum loss of face. The secretary was deeply perturbed by my attitude. So history was made, and we hope that nuclear weapons would not be used again in human history, even though we are under the threat of its being used again as a consequence of the war in the Ukraine. I write here some information about the events that you may like to read. Appendix 4, for instance, would show us what will happen if we had a fireball of an 800 kiloton nuclear weapon exploding over the island of from the Bulletin of Atomic Scientists over a large city like Manhattan Island in New York, for instance. And we hope that those nuclear weapons will only be used in peaceful applications in general. I'll stop here and stop the share and go to the chat room. If anybody has a question about our first chapter here, the birth of the nuclear age. We'll follow it by another chapter now that describes how the kiloton level of release of energy in nuclear devices was followed by a 1,000-fold, 3 orders of magnitude higher energy release when thermonuclear weapons were, of course, discovered and tested. And we live under the threat today. It's not the threat of kilotons levels of energy release. We are talking about megatons, millions of tons in a single device. Good morning, everybody. Is there no homework today, or has the PDF just not been updated yet? You give me 24 hours, please, to write those assignments, depending on what the lecture has been, what I was able to cover in a given lecture. And I give you 1 week to turn in the assignment. So you can turn it immediately after I have written it. It involves lots of programming using HTML and so on. So you give me at least 1 day to get it done. It's attendance required. I'm asking because I'm doing a program next month that will make it difficult me to attend the lecture. Attendance definitely is recommended. That's why we are using it face-to-face. There is no replacement for the lectures being face-to-face, but you can miss, if you miss a lecture, we go through the trouble of recording it, and the way to access it is shown to you in the list of assignments on the web page. Okay, any other questions? No more questions, so I'm going to not waste our time and go and share the screen again. And in that case, we move to the next chapter, which involves really the situation today. We are not at the situation of the kiloton level of energy release. As I said, we have now a situation where we can release megatons levels of energy. So the destructiveness, if nuclear weapons are used, and can be basically what we mentioned in the preface, according to Mr. Enrico Fermi, one of those filters that can end our technological civilization in general. So the first success of the first man-made self-sustained chain reaction in Chicago pile number 1, followed by the Manhattan Project, which culminated in, of course, the bombing of Hiroshima and Nagasaki, was addressed by smart people, and the consensus has been that humanity has to emphasize two new directions. First, sublimating the new state of knowledge, and quoting the Bible, the Holy Bible here, same as the Israelites when they got into the Holy Land, basically turning their swords into plowshares. And the energy released from nuclear devices definitely is better used for nuclear peaceful applications. Primarily today, it's the use of nuclear energy for producing electrical power. There are other possible peaceful applications, like the desalting of seawater. You can boil seawater, or use electrolysis, or use other methods like reverse osmosis to turn salty water from the oceans into fresh water. And there is a shortage of fresh water in the world that is more important than there is no shortage of electricity. And of course, the second approach is to contain the possible, hopefully improbable, but it's becoming very probable, close to probable than possible. Possible is not the same as probable, of course. Use of nuclear weapons through different treaties and international agreements. The primary one is the Nuclear Non-Proliferation Treaty, where nations of the world agree to not develop nuclear weapons in return for the nuclear power states to help them develop peaceful nuclear energy. Interestingly enough, the NPT, or the Non-Proliferation Treaty, also commits the nuclear power states to eliminating nuclear weapons, but it is not happening. So we have now a new world, and in January of 1946, the General Assembly of the United Nations met and created the United Nations Atomic Energy Commission, that became the precursor for what exists today at the International Atomic Energy Agency. It is located in Vienna, in Austria, with a charge of eliminating all weapons of mass destruction, not just nuclear weapons, but weapons of mass destruction include also like chemical weapons and biological weapons. There is a suspicion that the COVID-19 that we all lived through and survived it was a result of what's called gain-of-function research, GOF, which is a disguise of creating biological weapons. So that is another filter. Other than, say, global warming, we have now nuclear war, as well as the gain-of-function research as filters that can end up our civilization, technological civilization. These are pictures of the Trinity test. You could see a sequence of the test creating a fireball. The fireball reflecting through the ground. It was exploded on top of a tower. So the reflection creates what's called the stem wave that propagates horizontally and leads to a large destruction. This is an actual picture of the test, the Trinity test in that case, in color. And it is the only picture taken in color of the process itself. As the nuclear testing occurred after the bombings of Hiroshima and Nagasaki, testing in the atmosphere continued in the United States, particularly at what is called the Nevada test site. So if you lived in Las Vegas, you could see the explosions on the horizon. And here are people on a hill in the vicinity of the city of Las Vegas, kind of car, basically watching, leaving their cars and pickup trucks on the front, watching a nuclear test being conducted in the atmosphere at the Nevada test site. Las Vegas, as you know, is 65 miles away from the Nevada test site. This is a mother and her son from their home watching an actual explosion in the air, also the mushroom at the Nevada test site. That was in 1953. The whole thing was some kind of great interest. So you could see here a ballet dancer dancing where there was an explosion occurring in the sky. And this is again another explosion in the sky. And these two pictures are for basically, the process became very glamorous and people like to watch it and talk about it. But Lee Merlin was named Miss Atomic Bomb in the Nevada desert, and she has her dress here, but she had a mushroom made out of cotton. It was some kind of glamorous, and people were interested in it. They didn't know the effect at the time. The United States Navy became very concerned about the repetition of the bombing at Hawaii of the American fleet at Pearl Harbor, and they were worried about it. So they went into a testing process of what would happen to a fleet in a harbor as a result of a bombing using a nuclear device. So they used atolls in the Pacific Island. You could see here an atoll is basically an island in the open to the ocean at some point, but it has a lagoon in the center where ships can seek refuge from the storms in the Pacific Ocean. So that is a location of one of the tests. You could see here the picture shows some ships, decommissioned ships from the Second World War, being tested as to the effect of a nuclear bombing similar to Pearl Harbor. And you could see that this is a device that was exploded underwater. This is a silhouettes of the decommissioned ships at what was called the Baker test. You could see here, let me see, the Crossroad Baker tests. It was this very small device, fission device, 21 kiloton of TNT equivalent. And basically it was surrounded by a fleet of 96 decommissioned naval vessels. And the atoll was named the Bikini Atoll and then the name became the name of the swimming suit that was some kind of designed by some French swimsuit designer. The test in that case happened on July 24, 1946. Notice the silhouettes of those decommissioned mothballed ships. And here is a succession of pictures from a video. The device, 21 kiloton of TNT. This is the same as the, let's see, that would that be the Nagasaki kind of a level of energy release. The explosion was done underwater with the fleet of ships surrounding it. You could see here the water, instead of having a fireball, now the water has been evaporated. So it's steam kind of a ball rising up to the sky. Millions of tons of water rose up, and then they did not remain up, they fell down. as they fell down, you could see here one of the ships basically totally carried out of the water. Here it's shown again, and then fell down on the ships that were left on in the test itself. The test lifted 2 million tons of seawater. It created a huge base surge, 274 meters in height, and its tsunami, 5 meters in height, hitting the ships to the point, as you could see here, that they were raised out of the water. Some of the ships had animals to check the effect of radiation on them. These are goats here, for instance, on ships to test the effect of radiation. The effects of radiation were not known at the time. This is the Bikini Atoll fleet of decommissioned ships used in the nuclear testing. They were all old ships from the Second World War, and even some of them were Japanese ships, and one of them, Prince Eugene, was a German ship. One of the tests involved exploding a device on top of an aircraft carrier. That's the Independence aircraft carrier. You know that the decks of aircraft carriers are made out of wood to get the impact of the basically the plane that is landing on it. It was total destruction, as you could see here. The device was exploded 150 meters above deck. That was November 2nd, 1952, not the 50s in general. Another aircraft carrier, the Saratoga, did not last too long. In fact, you could see that after 8 hours, the whole ship sunk down into the water. So nuclear devices are a great threat for an aircraft carrier fleet. This is one of the test ships, Pennsylvania. It was an old ship that was decommissioned. Some Japanese ships were used, the Sakawa, and another one was used, was Prince Eugene. Oh, that's a Nagato. The Nagato was the largest cruiser ever built in history. It was built by Japan. It was also used in the testing. And then you have the Prince Eugene. That is Prince Eugene ship, was also sank also in the process. Now it became some kind of an interesting target for scuba diving enthusiasts, because large populations of fish have now populated the sunken ships in the Bikini Island. There were attempts at decontaminating the ships there because they were covered by the water from the explosion, so they had lots of fission products as well as plutonium kind of contamination. This process failed miserably, so the destruction from the shock wave destroyed most of the components of the ships, and just getting the radioactivity washed out was not sufficient. The United States Army exploded devices and had basically soldiers walk. Initially, they were in trenches, but then they had them walk into the area of the explosion to train them to basically operate even in a nuclear war situation. Mannequins were used to see what is the effect of the explosions on people. The Air Force had their personnel sit using ski kind of goggles and watch the explosion itself. And the ski goggles there were supposedly protecting their eyes against the ultraviolet radiation. Navy personnel were also asked to wear goggles and watch the explosions from their ships. The idea was to familiarize them with the possibility of nuclear war. Here it shows the Army troops watching an explosion and then walking into the area of the explosion, which exposed those personnel really unnecessarily to radiation from the explosion. Another group of personnel also watching those explosions in the Nevada desert. Those people there were unnecessarily exposed to the X-rays radiation, the gamma ray radiation, and the neutron radiation. They were used as guinea pigs, and the rest is unfortunate. When an explosion happens at high altitude in the sky, It doesn't generate the fireball that we see on the ground. It is only the product of the device itself. It creates a different kind of a mushroom, and it creates a very strong electromagnetic pulse, and we call that the EMP, electromagnetic pulse. That electromagnetic pulse is similar to lightning, and it can generate such high voltages that it can affect electronic devices on the ground. And there is a movie, I think, where aliens supposedly use an electromagnetic pulse to destroy all the maybe the solid state devices on cars. And a single explosion supposedly can generate, a nuclear explosion can generate a huge electromagnetic pulse on the, if it is exploded over the continental United States, to turn back the whole United States back to the Stone Age, because all our electronic devices in cars and refrigerators, TVs, and any water supply systems, electrical supply system will stop operating in general. Low altitude testing was also tested. This is a blast effect, not high altitude, but above the ground. So you don't find that mushroom device resulting from the explosion, but you get those fireballs, and somehow they're artistic in shape for the photographers. This is a result of a high altitude test fireball, no mushroom in that case. And the concern, as I said, is the electromagnetic pulse. So it's the same as lightning. One of those tests occurred in the Pacific and close to the island of Hawaii. And you could see here that is the island of Hawaii. Now, the observation is that they can cause auroras, aurora borealis, and like the auroras that happened from the effect of the solar wind, and it destroyed many of the street lights on Honolulu in Hawaii. This is again testing of the Air Force personnel. Some of them were smart enough to have some plastic covers, but they lined up all those mothballed airplanes, and they had them sit there watching the explosion. This is the picture from the light. They exploded the device up above the planes on the ground, but the personnel were forced to watch the explosion. This is a very famous device that brought in the definition of ground zero. And these 5 gentlemen there stood there when a plane exploded a nuclear device up in the sky. And the shot was called the Genie shot. They were unnecessarily exposed to gamma rays, X-rays, ultraviolet light, and infrared radiation, followed, of course, because the electromagnetic radiation, the X-rays and so on, move at the speed of light. So you could see the light irradiating them first, and then comes the shock wave and hits them. And here, if you read this carefully, let me magnify it. That is the first definition of ground zero population. So that was a device, small, a miniature device, 2 kiloton, exploded overhead by an F-89 Scorpion fighter jet at 10,000 feet in height, and the miniaturized device was 2 kilotons. Devices that would be used as shells for cannons are also used. You could see the spherical shape here. That would have been a plutonium shell put into a high bore kind of cannon and exploded. That's called, I think, the Grable test here. Yeah, Grable event. It was an operation called Upshot Not Hole. Was an air detonation from a 289 millimeter artillery gun. That was in 1953. The device now, the shell is designated as a W79, 8-inch. Testing happened from the perspective of the possibility of nuclear war. They built a whole city, in fact, at 1 mile away from a test, and you could see what happens to a residence if you are explode a device 1 mile away from it. First, at the speed of light comes of a light pulse. This is followed by X-rays. The X-rays are absorbed in the surface of the structure or the building, the home in that case. It starts immediately a fire from heating it. After the X-rays come the neutrons, and then comes the blast wave. So now, as the structure is on fire, comes the blast waves, and it subjects it to a compression wave first. So it pushes all the structure to the right, away from the site of the explosion. But shock waves in that case are also followed by a rarefaction wave, because you create a piston. So you gather the molecules of air in the front as a piston, and behind the compression wave, you find a rarefaction wave. So that house now is pushed by to the right, away from the explosion by compression wave, and then comes the rarefaction wave that pushes it in the opposite direction. So you push it out and then push it in, and that results in the complete destruction, total obliteration of the structure. You could see the whole thing exploding, and it is also on fire. So that is, again, the effects of nuclear weapons. That is what you end up with in the end. So the X-rays cause the ignition, a fire, and the infrared, of course, is heat. That's 3,500 feet from ground zero. It's 1.5 miles. 1 mile is 2,450 feet. That was March 17, 1953. Again, these are all pictures from the Nevada site office. They are public domain. They studied the effect of explosions on forest areas. You could see here that an explosion coming from the right pushes the trees to the left as they are being ignited, turn them into a fire. And then the shock wave goes in the rarefaction, pushing them into the other direction. So if you have a person or an animal here, he would be flying up to the left, and then it will be brought back again to the right with the rarefaction wave in the shock wave that they're subjected to, and the whole thing would be on fire. This is testing on ships' components. That's a radar dish here, and you could see being subjected to the shock wave obliterates all the equipment on top of a ship in general. All right, so that was testing, and the testing primarily was on the effects of fission devices, where you use uranium-235 or plutonium-239. Came in a scientist, now the effort was done by Robert Oppenheimer and General Leslie Grove, but came a scientist on the Manhattan Project, Edward Teller, in that case, and he suggested that the Russians have caught up on what the United States was doing in with nuclear devices, and he suggested that more energy can be generated by fusion devices, and we'll discuss that as we go along. The effort in the United States was being spied upon. For instance, one gentleman, Klaus Fuchs, was from Germany, but he went to England and came back to the Manhattan Project. He had ideological kind of thought that the knowledge about nuclear weapons should not only in the hand of one single nuclear power state, the United States. So he communicated the information to the Russians. And Robert Oppenheimer objected to the effort. He said that we don't need really nuclear devices that would generate a yield of more than 100 kiloton of energy release, because that will destroy any kind of military installations, and there is no need to go beyond that level of energy. Edward Teller basically objected to it. It became a big clash of different personalities. Edward Teller against Robert Oppenheimer. Edward Teller was very nasty. He accused Robert Oppenheimer of being a Russian spy. He ended up having, they withdrew his security clearance. They really brutalized him to a certain degree. And the effort of Robert Oppenheimer with Leslie Grove was at the Los Alamos National Laboratory. So Edward Teller went to the Air Force, and the Air Force helped him establish the Lawrence Livermore National Laboratory in California, just to pursue the idea of using fusion in a nuclear device, not just fission. And the code name for the project was named the Super Project. They tried to use a nuclear device to heat up the fusion fuel. In that case, the fusion fuel would be primarily lithium deuteride. Lithium is an isotope, has two isotopes, lithium-6 and lithium-7, and deuteride would be like lithium hydride. It's a powder, and the hydrogen is replaced by deuterium. The neutrons from a fission device would interact with the lithium, and the reaction that occurs produces tritium. So now you have two isotopes of hydrogen, the deuterium containing a proton plus a neutron in the nucleus, and tritium containing one proton and two neutrons in the nucleus. Those two isotopes, if heated to high temperatures from a fission device, can combine together and produce more energy per unit mass than a fission device. So they conceptualized the device as heating a cylinder of liquid deuterium to start the fusion reaction. In fact, they tested it, and it was successful to a certain degree. I will bypass that part here about the radiation effects, and the problem was how to initiate a thermonuclear reaction. And in that case, it is really what you call a hydrogen bomb, because of the two isotopes of hydrogen, deuterium and tritium fusing together. They tried different processes. They built computers. So computers, in fact, that we have today were a spin-off of the effort of creating a thermonuclear device. We had a computer built here on the campus of the University of Illinois. It was named the ILIAC for Illinois, some kind of computer. And several ideas were tested on to initiate a thermonuclear reaction by Edward Teller and his group. One due to a scientist called Gamov, and it is referred to as squeezing the cat's tail. Another idea to ignite the fusion reaction was by a mathematician, Stanislav Ulam, referred to as a spittoon, and one to Edward Teller himself, referred to as the womb. And Mr. Gamov, in a book that he wrote, The Curve of Binding Energy, that you may find at the undergraduate library if you are at the campus of the University of Illinois, you'll find that he put that into a diagram that we'll look at very quickly here. Here is a diagram that Gamov put in his book, The Curve of Binding Energy. He shows himself here, that's Mr. Gamov, holding a cat and squeezing its tail. He shows Edward Teller here with what's called the naha. It's some kind of ornament that the Navajo Indians in the area of New Mexico would wear around their neck. And he shows Stanislav Ulam spitting into a spittoon. You see those spittoons in the cowboy movies, late night cowboy movies, where they chew the tobacco in the saloons and then spit what's left in those spittoons. All right, so these are the three ideas here: squeezing the cat's tail, the naha ornament, and spitting into a spittoon. On top in the picture, he shows here Joseph Stalin carrying an atomic bomb. That is after the Russians eventually exploded their own atomic bomb, imitating the United States. And he shows here Robert Oppenheimer with a halo around his neck, looking like an angel, who was in fact really objecting to the ideas of Edward Teller. They tried each one of those processes and simulations on the ILIAC computer, and that did not lead to the ignition of the fusion part of the device. They tried the spittoon, it doesn't work. But Stanislav Ulam, in his book, History of a Mathematician, I think you can find that also in our bookstore. And it came out that igniting a hydrogen bomb was a combination of those three processes, where you explode the device at the focus of an ellipsoid of revolution. The energy concentrates itself at one end. It ignites the fusion fuel and leads to a fusion reaction between deuterium and tritium, like what happens in the sun or the stars, where hydrogen nuclei fuse together and produce helium-4. And you can squeeze a long cylinder by its tail, and the explosion can propagate in a long cylinder, that we'll show. And in that case, you can produce not the kiloton level of energy release, but the megaton, millions of tons, 3 orders of magnitude higher level, which we call the hydrogen bombs or thermonuclear reactions. Edward Teller describes the realization of the possibility of this development as, quote, "By the end of 1950, I had the novel and positive answer. Because of the wartime work, we knew how to strongly compress a thermonuclear fuel, and in the compressed fuel, radiation would be less important and would not inhibit the reaction." This is a picture of that Navajo necklace that was worn in the picture by Gamov. It shows really a squash blossom and 2 healing hands. And this is what one can conceptualize as that the Ulam, what became known as the Ulam-Teller configuration, which is a combination of the 3 ideas that I just described. So you start with a long cylinder. You start really with an ellipsoid of revolution, like shown here. At the focus of that ellipsoid of revolution, you explode a fission device. You place a shield here. You'll find that the radiation from that focus reflects from the wall of the ellipsoid of revolution into the other focus, from that focus to this focus. Any radiation reflects and comes to that point where you ignite a small amount of deuterium and tritium. You create, in that case, a wave, lots of radiation that goes into polystyrene in a process, in a device that you call now a Hall round. The radiation pressure would accelerate a container that contains lithium-6 deuteride. Lithium-6 gets neutrons that are emitted from the fission device. The nuclear reaction, as we'll see later on, produces tritium. Both the deuterium and tritium now are compressed. In the center, they had what they call a spark plug, a long cylinder of plutonium-239 or uranium-235. That lithium-6 deuteride now sees neutrons from the fission device as well from the spark plug. And in that case, it has such a very high temperature and very high pressure that you generate a fusion reaction between deuterium and tritium. The interesting thing is that you can make that cylinder here as long as you can, as you want, in fact, and the wave would propagate into the cylinder, and you can produce, in that case, megatons energy released from a fission, fusion, and then they make it act like a multi-stage amplifier. The casing here, if made out of uranium-238, will get neutrons generated from the DT reaction here that are energetic neutrons. They move at 14.06 million electron volt. Now they can fission the uranium-238. So you get a fission device of very small yield, 20 kilotons maybe, that ignites a larger device of a fusion system, and then the neutrons produced there can also fission the casing, and you end up with 1 million of tons of TNT. And you, in addition, you can make that cylinder as long as you like here. So it's like igniting the tip of a cigarette. And that became known as the Ulam-Teller configuration. This is my drawing here. That is supported by another author, Weinberg, I think is his name, where he shows that ellipsoid of revolution, the radiation from the atomic bomb concentrating from one focus to the other and propagating in the polystyrene or foam, just plain foam, into a long cylinder that contains lithium-6 deuteride. He's not showing the spark plug, but he suggests that the casing could be uranium-238. This diagram and this diagram both show that they used lithium-6 deuteride. And so they had to build a plant at Oak Ridge, Tennessee, to separate that isotope of lithium, lithium-6, from lithium. Later on, they discovered, as I'll discuss it in the notes, that they don't need really to use lithium-6. Lithium would be fine. And all the effort was based on the non-knowledge that neutrons can also interact with lithium-6, producing more tritium for the device itself. That device, as I suggested, was tested in different ways. Let us just quote Stanislav Ulam in his book, Adventures of a Mathematician. Maybe you can find it at the undergraduate library also, other than the Gamov book. Quote, perhaps the change came in with an idea I contributed. I thought of a way to modify the whole approach by injecting a repetition of certain arrangements. Unfortunately, the idea or set of ideas involved is still secret and cannot be described here. And that became known as the Ulam-Teller configuration, and people simply somehow try to speculate what is that configuration. And this is basically the whole idea of it. But engineers and scientists in the national laboratories who deal with weapon devices basically end up spending lifetimes improving on the processes involved in that type of an explosion. But it covers the diagram in the by Gamov right here. You could see the ellipsoid of revolution, the idea of Edward Teller. The spittoon here is the radiation being transferred from the fission device to the long cylinder. The fission device would be called the primary. The long cylinder would be called the secondary. And Mr. Gamov here squeezing the tail of the cat, making it shiver maybe, would be propagating the fusion wave into the long cylinder of the device. And in that case, because it's a multi-stage amplifier, you can start here with a small explosion, 2 kiloton maybe of TNT or from plutonium. You see they're having a shape of, I put the shape here, this is my own drawing, a shape of, let's say, a shell, and you propagate it into as large as a mass that you want. The Russians exploded a device that they designed, and when they discovered that it is going to release 100 megaton, 100 million tons of TNT, they reduced that fusion part in it and reached the highest ever energy release from a nuclear device at, I think, 65 megaton. They discovered that if they explode the 100 megaton, the plane dropping it would be obliterated or dropped off the sky, and the shockwave would affect Moscow, and they exploded it in Siberia. So this is what we are living with today, not kilotons like what happened in Hiroshima and Nagasaki, but now we are living with megatons. The nuclear reaction that we'll study later in more detail that occurs in those thermonuclear reactions. Thermo, because it depends on the heat generated from the fission device, and nuclear, of course, because it's a nuclear reaction. We use the isotope of deuterium plus the isotope of tritium. A nuclear reaction occurs where a neutron is released, and a very high energy neutron that can now fission uranium-238, the casing in the third stage of what we call the multi-stage amplifier, and an alpha particle generator. The reaction produces 14 here plus 4, about 20, say, million electron volt of energy. Compare this to the energy released from a fission event, which is 200 million electron volts of energy. So fission is energy rich, but neutron poor. The neutrons from a fission reaction comes out, as we said earlier, at 2 million electron volt only of energy, whereas a neutron from a fusion reaction comes out at 14 million electron volts of energy. You can use what's called the neutron multipliers in the device. A neutron would interact with beryllium-9, produces 2 neutrons, increasing the efficiency of the device, and sometimes beryllium has been used for that purpose. This is the first ever thermonuclear device exploded. It was a very large cylinder, as you could see here. And in that case, they did not use that D plus T reaction, but they simply used liquid deuterium. So the liquid deuterium can result in the fusion of the deuterons in that case, and producing neutrons and tritium. And see the size of that cylinder here. These are 2 gentlemen sitting there on the seats, and it was huge in size. They had tubings that to measure what are the reactions occurring. They placed several atomic bombs inside the liquid deuterium. So it was a cryogenic system that cannot be deliverable. You cannot put a cryogenic factory on an airplane or a rocket. But they simply were testing the use of deuterium. So in that case, only deuterons were used. They show us here the Ulam-Teller configuration, the spark plug that I showed in the diagram earlier, the fusion fuel surrounding it, the shield from the ellipsoid of revolution, and several devices. The starting one is there at the top. So this device was named the Mike device. It was 22 feet in length and 5 feet in diameter, huge in size, and they exploded it again in one of the atolls. What is an atoll? It's basically an island famous in the Pacific, primarily not in the Atlantic, but in the Pacific, where a coral reef forms a barrier protecting the inside from the storms on the outside. So that was used by the Polynesians and people in that area, fishermen, to moor their ships, but then go out to the outside world and do their fishing. This is the explosion of the Mike device. It was a monumental, really, success. It generated the level of how many megaton? 10.4 megatons. So we're not talking kilotons now. Remember, Hiroshima was 15 kilotons. Nagasaki was 21 kilotons. Kilo is 1,000 as a Greek prefix. Here we are talking 10 million tons, 3 orders of magnitude, 1,000 time the energy release. It did not happen in that case at the same atoll as the previous tests, the fission tests, but at another atoll named the Eniwetok atoll. It was 500 times the yield from the Hiroshima device, and that happened in October 31st, 1952. It generated a mushroom cloud that reached 100,000 feet into above the Earth's surface, beyond the atmosphere of the Earth in general. In a enhanced radiation weapon such as this device, where you don't use the 3rd stage, in that case, a fusion reaction produces very highly energetic neutrons. If you don't use the uranium-238 casing, and this is what you heard about, maybe is named the neutron bomb. So the neutrons become really the main objective, and neutrons can penetrate fortifications underground and tank walls and cause great harm. The casing would be out of lead, beryllium, tantalum, or tungsten. So these are all heavy elements, but some people suggested that, well, if you are going to generate such a huge energy release, they worried about a reaction happening in the atmosphere of the Earth. In that case, you could ignite the nitrogen. Remember that 15% of what we breathe in our atmosphere is oxygen, and the rest of it, 70%, is nitrogen. So they thought about the isotopes of nitrogen 14 would fuse together, generating magnesium and an alpha particle. And in that case, the atmosphere of the Earth would ignite and turn the Earth into a star. Well, as you could see, they worried about it, but it did not happen because we are surviving. We have survived it as a human species, and we are still talking about it. The use of deuterium as a cryogenic, basically liquid hydrogen or liquid deuterium, is not a deliverable device. The Russians exploded a device in which they used a powder. The powder was in that case, lithium hydride. That's a powder rather than using deuterium plus deuterium. And the United States immediately imitated the process. And in that case, lithium deuteride was used in another test. It was named the Bravo test. And it was conducted in 1954 and generated even more energy than the deuterium device, 14.8 million tons or megaton of TNT. You could see here now that the Ulam-Teller configuration was used. On that side of the device here, on this side, you would have the spherical kind of efficient device with a shield, with a styrofoam on the fusion part. So that is the primary, and this is a secondary, and it used the Ulam-Teller configuration with uranium temper that generated really 80% of the yield. So those fusion neutrons now can multiply the energy release several fold, 100 folds from just a fission device. And the fascinating thing is that that was such a huge device. It was placed, you can see that gentleman here, it gives you an idea about the size, on a barge and exploded in that case back again into the Bikini Atoll. You could see here the mushroom. The meteorologists thought that the winds will be blowing from that side to the west in the open ocean, so that radioactivity would be lost there. That did not happen. The wind, this is the atoll here. You could see the coral reef kind of an island. The wind blew the fission products to the east and covered an area of 5,000 square miles. Unfortunately, those 5,000 square miles contained several islands that were inhabited by people. They hoped that the wind will blow to the west. It blew, unfortunately, to the east. So they had to, the fallout or the products of the explosion fell down almost in the shape of what looks like dust or like snowfall, and came in on the surface of the skin of the inhabitants and caused burns from the emission of beta particles, in that case, like electrons. There was an observation site shown here, and away from for the Bravo test, away from the explosion. The people there were evacuated by helicopter. Why? It turned out that the test did not just produce the amount that they expected to release in energy, like about 5 megaton. It was double or triple the energy release. So they had to evacuate the people who were observing the test by helicopter. They had bed sheets over their head to protect themselves from the radiation. And that was in the Bikini Atoll. Today, the Bikini Atoll is some kind of a tourist attraction. It says here, welcome to the beautiful island of Bikini Atoll, Republic of the Marshall Island. So that was history. And so there were observers on a ship, the Curtis ship here, all those people observing the event, other than the people in the in that bunker, basically, that were evacuated because the energy release was much higher. And on the east of the explosion site, the Bikini Atoll, a Japanese ship named the Lucky Dragon here, kept in a museum, in fact, in Japan. It was affected by the Bravo test site. They were fishing tuna. The tuna was taken to the markets in Japan, but then they discovered that it was affected by the radiation. They removed it. But one of the fishermen on that boat was exposed to the fallout that looked like snow, and he was They was wondering, what is that snow in the middle of the Pacific Ocean? One person died in the process, one of the sailors on the ship. So that led to an evacuation of those islands that were inhabited, where the fallout found its way. It was a dilemma that I describe in another chapter. If you have time, we can cover it on the environmental effects of fusion and fission energy. Basically, the population was relocated from the Bikini Atoll. They were returned back again. The radiation was too high. They took them back to other islands. They put them in islands rather than atolls, so they couldn't go fishing and carry on. It has been some kind of a huge drama in general. So as I suggested, the yield of the Castle Bravo came out about 15 megatons of energy. The calculated energy release was only 5 megaton. So what is it that they got the 50 megaton here? I try to explain it. And the explanation comes in is that they use lithium-6 deuteride. And the reaction that happened with neutrons with lithium-6 is that it produces an alpha particle and a triton, an isotope of hydrogen. And that triton now would be combined with deuterium in the lithium deuteride, generate a neutron and release 17.6 million electron volt of energy. They did not take into account the fact that lithium is primarily lithium-7, and they didn't have data about what is the reaction of neutrons with lithium-7. This is the reaction of neutrons with lithium-7. With lithium-6 first, that is a reaction here that produces a tritium that would fuse with a deuterium. But a threshold reaction, if the neutron's energy exceeds here, you could see here that's 1. So if it exceeds 0.2, 0.3, 0.5 million electron volt of energy, you'll find that lithium-7 isotope also produces a neutron. And they didn't take that into account, and that led to a triple yield. So they went through a big trouble producing the lithium-6, separating it from lithium-7 using mercury. And then an amalgam is produced by the lithium-6 and the mercury. Then you heat the mercury to release the lithium-6. They built a whole plant at the area of Oak Ridge, Tennessee, but they didn't need to use it at all as lithium-6. They could have used simply lithium. The lithium-7 reaction, in fact, is endothermic, meaning that it absorbs of energy. We'll go through more detail later on how those equations are balanced if you didn't have them already in one of your physics classes in general. So you'll find that this is the cross-section of the probability of interaction with the lithium-6 isotope, and this is the one with the lithium-7 isotope. So if you have neutrons of high energy, you are also producing tritium from lithium-7. And in that case, the reaction happens with lithium-7. So if we take the lithium-7 isotope, the lithium-6 isotope, and 2 deuterons, you'll find in that case that deuterium plus lithium-6 plus lithium-7 gives us 4 helium, 4 nuclei, and a neutron. The reaction, of course, that you know happens in our stars, the sun, and other stars, not all of them, is basically 2 hydrogen atoms turning eventually into helium-4. So on Earth here, we used a different reaction that happens much faster than the 4 hydrogen leading to helium. We do like what happens in the stars, but using deuterium and lithium, producing helium back again, and neutrons are released in the process. I discuss again what is it that why is it that they got 3 times the energy release in the reaction. This could be the topic of his thesis to explain the process. I talk about other reactions where, but we'll cover those reactions later on, and even try to describe some anomalous amount of lithium that exist in the universe. I suggest that they have been part of some nuclear reactions. Now, here we have now a way of producing tremendously large amounts of energy beyond, way beyond 1,000 times from fusion rather than what you can get from fission. As you could see, of course, humanity is using today fission to produce electrical power, peaceful application there. In the future, we'll use it for freshwater supplies, but they use it as a destructive device, hopefully will never be used. This is the size of one of those devices that would use fusion. They called it the MK17 device, 25 feet in length, 21 tons in weight. Look at this gentleman here, a huge device using really delivery vehicles, huge bombers to do it. However, in today's world, those devices have been miniaturized. Miniaturized to the point where, look at this two gentlemen here carrying, in fact, a fusion device. And you could see here the spherical part is the fission or the primary, and the cylindrical part would be the secondary. It is not very heavy. In fact, let me see, that's 290 pounds or 130 kilograms. And that device can be carried by a Tomahawk missile. And they call that device a W80 device. Again, you could see it very clearly, the Ulam-Teller configuration, the spherical plutonium maybe primary, and this part here is the secondary as fusion, and that device can produce the equivalent of, I think, 100 kilotons of energy, 170 kilotons of thermonuclear energy carried by a Tomahawk missile. So it's very miniaturized, and this is the way it shows up. There are the information. The United States produced even much larger devices. So that one is a 9 megaton of TNT equivalent device. See how huge it is, the gentleman pulling it here. And that was designated as the P-53 device. And it was produced and stored at the Pantex plant. These have been eliminated from the American stockpile. There is no need whatsoever to use a 9 megaton device, destroy a whole metropolitan area. You destroy the whole area of Chicago and all the way to Milwaukee in a single device here, and can wipe a whole city like whole London or whole of New York. There is absolutely no use for it. And then it's also it is a war crime to target population centers in war in general, whether it's a nuclear devices or conventional device. As devices have been miniaturized, this is a schematic of a 5 to 80 kiloton W85 device. Now, why do we say 5 to 80? Because a general can decide whether he wants an 80 kiloton release of energy or a 5 kiloton release of energy. If he uses only the fission component, it will release 5 kiloton of energy. Miniature device, 1/4 the size, the yield from the Hiroshima device or a Nagasaki device. But if you add tritium to it, you induce that fusion reaction. You get neutrons that are very highly energetic, 14 million electron volts, and the fusion part now can produce all the way from 5 kiloton of energy release to 80 kiloton of energy release. And that's why tritium becomes a major component of modern day nuclear devices, is that you can control the energy release. However, it is something that has to be developed on an industrial, basically an industrial scale. So you get lots of companies generating many of those components. Each one of those little pieces there is generated by a different industrial process. Came in a gentleman at the in Madison, Wisconsin, in a magazine called The Progressive, and his name was Moreland, and he came up with a description of what basically what we have described as the Ulam-Teller configuration, and he published it in the magazine. He suggested that the fusion part is ignited or is compressed using soft X-rays. That led to an uproar by the Department of Energy against the magazine, The Progressive, There was a copy of that article in the undergraduate library that I sought and read, but it has disappeared somehow, basically stole it. And this is the configuration he gives us for it. He would suggest that it would be a levitated core of plutonium-239 and followed by explosive lenses, a shield, the spark plug, the fusion part, and the styrofoam that generates basically high pressures, radiation pressure that compresses the fusion part of the device. Here at the bottom, he's talking about a casing, a container that would adjust the yield by using tritium and deuterium gas reservoir. So in that case, this is just to ignite, to control the yield of the device. They use beryllium as a reflector of neutrons, and that caused an uproar in releasing the secret of how to compress that lithium deuteride, in that case, as a powder by using the soft X-rays. Well, the release of that information has been useful in what we are going to talk about by the end of the semester here, or the when we deal with fusion. The idea of using soft X-rays is now being used in the process that would cause us to generate fusion in a controlled manner in what we call inertial confinement fusion. This is another way that people display the interior of Mr. Moreland's the description of what the Ulam-Teller configuration is. You could see the fission device here, the styrofoam, the lithium-6 deuteride, and the spark plug here in the center. And his article, he wrote a book. The book is titled The Secret That Exploded. Somebody should go to the undergraduate library and tell me whether they can find the book, and if anybody is interested in reading it, can read it. Other than the Ulam-Teller configuration, came up a new configuration that looks like a peanut now. And that peanut configuration gets a fission device, say uranium-235 or plutonium-239, and that is exploded in one side of the peanut shape. The radiation would compress, actually the fission device is shown here, plutonium-239. The radiation generated as X-rays would compress a fusion device on the other side containing lithium deuteride. Now it's not lithium-6 deuteride anymore. The secret basically is out of like the Aladdin device. And this is used in what's called the MIRVed devices. This is multiply independent vehicles that you can have up to 12 or even 15 of them at the tip of an ICBM, multiply independent targets. In that case, each one of those, Oppenheimer was right, can be only 300 kilotons of TNT equivalent. They are used on intercontinental ballistic missiles, ICBM, and that is used on the MX international device. Some authors show it in a different way, in that instead of having the fission part in the back, they have the fission part in the front, plutonium-239. This would be more balanced from the perspective of basically center of mass, because the plutonium would have a higher weight, but the shape of the peanut is shown here inside the device, the MIRVed device. And here they say the booster gas would be the tritium that we mentioned can adjust the weight. Another way of showing it is again the plutonium in the front here in the shape of an egg ignited from one side only, and the fusion part as the second part of the peanut in general. And this configuration here is actually suggests that this is truly the shape of the W59 1 megaton device. All those fission devices take that shape of the Ulam-Teller configuration or the peanut shape. These are all devices, nuclear warheads. The warheads also have been generated on a very small scale as demolition munitions to destroy just maybe 1 kiloton only to destroy a bridge or a dam, like they destroyed the dam somewhere in the Ukraine. Something interesting here is shown that we'll describe next time is that those intercontinental ballistic missiles are claimed by the Boeing company making them, that they travel at 15,000 miles per hour. That's Mach 23. So that's 23 times the speed of sound. And the question is, how can you intercept them? Intercepting something that is hypersonic at moving at 23 times the speed of sound, it needs an interceptor that travels at the same speed. So next time, we'll start the next lecture next Monday, checking that assertion that those ICBMs really move at 23 times the speed of sound, and whether that's true or not. And have everybody a nice weekend. There will be an assignment posted, but give me a day to program it. It takes a long time to program those programs. The class is dismissed. You'll look at, read the chapters, of course. Reading is necessary to be able to solve the assignments. The assignments would be based on the reading lecture notes. Let me see here. Is there a homework today? Yes, there will be a homework today. I haven't written it yet. Attendance required? Yes, attendance is required, but if you miss one meeting, maybe you will find the recording. And do not guarantee that the recordings will all be successful. This has been always our problem with using Zoom, in that sometimes, oh, the recording comes out without the sound. And in that case, we cannot really publish it. How can we prepare for the exam? Should we memorize details from the history or calculations only? The exams will definitely come in the same shape or the same format as the assignments. So you should have read the material. The problems in the assignments are based on reading the material. So you are taking a class so that you can learn about the topic, and you become a part of an elite of people who know or understand how we can really control nuclear energy, both peaceful and war. Who can see? Jae Zong Jiang has a question here. I will be available to answer any question in the chat room, but the rest of the class can be dismissed. What is the question here? I don't know.